Professor Antoine Suarez is the founding director of the Center for Quantum Philosophy at ETH Zurich. A Swiss physicist, philosopher, and bioethicist, Professor Suarez earned his PhD in natural sciences from ETH Zurich in 1975. He is internationally recognized for his foundational work in quantum mechanics, including the co-proposal of the before-before experiment, which investigates quantum entanglement and non-locality using moving measurement devices. This experiment, performed in collaboration with Nicholas Gisin and others, demonstrated that quantum correlations arise from influences outside space-time, offering deep insights into nature of reality and causality. Uh, Professor Suarez, interdisciplinary research spans quantum physics, philosophy of science, and bioethics, with special focus on the measurement problem in quantum mechanics, the role of irreversibility in stable information formation, and the implications of quantum theory for free will and consciousness. His work explores how quantum mechanics might require new physics to explain the transition from quantum possibilities to definite outcomes, and he engages extensively with philosophical questions surrounding human freedom and scientific determinism. He is the author and editor of several influential books, including uh, Is Science Compatible with Free Will and Mathematical Undecidability, Quantum Non-Locality, and the Question of the Existence of God. Professor Suresh also actively promotes interdisciplinary dialogue on science and freedom, organizing expert meetings that bring together physicists, philosophers, and bioethicists to examine the relationship between science and human agency.
Uh, Many thanks for this kind introduction, and thanks also to Varun and Vasudeva and all the organizers for inviting me to this really uh, highly stimulating meeting. The topic is Beyond Space and Time, and I will summarize some experiments on entanglement, proving that quantum realm is beyond space and time. And outgoing from this result, I will propose the view of the quantum state as a real mental state, which relates a bit to the excellent lecture of yesterday by David Wallace. Well, causality in space and time. We often use remote control by means of radio signals. For instance, to send messages to the moon, to the ISS, to Mars, but we cannot act at a distance faster than light. Now you are seeing I am using remote control, you see, but this remote control takes some milliseconds to reach you in Kolkata. And so it takes also 2.5 seconds about to reach the moon, and it would take several minutes to reach Mars. Having this in mind, I will introduce you what is quantum entanglement, this quantum property, and quantum entanglement in the laboratory, in the lab. In quantum entanglement, a typical experiment on quantum entanglement in the lab, you have a laser source emitting photon pairs. One photon going to the lab of Bob and one photon going to the lab of Alice and being measured by meeting a polarizing beam splitter, each of the photons, and after meeting the polarizing beam splitter, the photon reaches either detector A1 or A0, B1, B0. And if you look at the side of Alice, then you will see that sometimes you get result 1, that means the photon reaching detector EA1 or 0, but absolutely random, 50% 1, 50% 0. Same thing at the side of Bob, 50% 1, 50% 0. And entanglement means that you are measuring the photon pair by one photon by Alice and one photon by Bob. If each measurement gives to you random results, then you would expect that it is random here, random here. So you would expect that you can get all the 4 possible result pairs, 1, 1, 1, 0, 0, 1, and 0, 0. This would be what you expect if you say we have randomness here, we have randomness here. So we would have about 25% for each of these possible results. Now, what tell us the experiment? The experiment show us that actually we get only the result 1, 1 or 0, 0. 1, 1, 0, 0. You then get 1, 0 or 0, 1 with the 2 polarizers oriented parallel in the same direction. Well, that is quantum entanglement in the laboratory, the phenomenon of quantum entanglement in the laboratory. So you see, it's like you would, Alice would toss a coin on Earth, and you note for tails, you note 1, for heads, you write 0. So you would get for Alice a string of bits which doesn't exhibit any particular pattern, 50% 1, 50% 0. Same thing on the part of Bob. Bob tossing a coin on Mars, and you have again 50% 1, 50% 0. But if you put both results, if you compare the results of Alice on Earth and the results of Bob on Mars, then you see they are perfectly correlated. This is quantum entanglement. This was the idea resulting from quantum mechanics that was very, Einstein was very upset with this idea, and this was on the basis of the discussions of this celebrated Solvay Congress in 1927. Here you have the founding fathers of quantum mechanics. You have Heisenberg, you have here Niels Bohr, you have here Max Born, and you have here Einstein. Here is Louis de Broglie. Here is Schrödinger. So all these guys are here. And the main discussion in this Congress was already launched by Einstein on quantum non-locality. The view of Einstein is well known and is very well expressed in a letter to Max Born by Einstein. Einstein writes, I cannot seriously believe in quantum entanglement because the theory cannot be reconciled with the idea that physics should represent a reality in time and space free from spooky action at a distance. So, you see, for Einstein, quantum mechanics implies spooky action at a distance. It is actually because you have randomness on the side of Alice, randomness on the side of Bob, but the same randomness. So Einstein's attitude was to claim quantum mechanics is incomplete, hidden variables are missing, the coins carry chips with hidden programs that produce the correlation. Similarly, like genetic twins are behaving the same in Kolkata as in Zurich because they have genetic programs leading them to behave the same way in the same environment. This was the idea by Einstein, expressed in a famous paper in 1935, the EPR paper written by Einstein, Podolsky, and Rosen, where Einstein presented this paradoxically result of quantum physics. The discussion on this issue of non-locality remains open. On the one side you had Einstein, on the other side you had the guys of Copenhagen, represented by Niels Bohr, and this discussion, this controversy between Einstein and Bohr remained open till the arrival of John Stuart Bell. He found the way to decide the controversy experimentally. And how work this? This work this way, instead of putting the polarizers parallel, if you put the polarizers with the angle differently oriented, then you will have, according to quantum physics, not always the same result, but you have sometimes concordance and sometimes discordance. According to quantum physics, depending on the angle of the polarizers, on the orientation of the polarizers, you will get, for instance, when you have the polarizers parallel oriented, angle 0, then you have, as we have already seen, you have 100% concordance and 0% discordance. But if you have the angle, the orientation in an angle with 30 degrees, then you will get concordance 75% and discordance 25%. And for an angle of 90 degrees, then you have concordance 0% and discordance 100%. Now, what is Bell's theorem? The ingenious idea by Bell was to make measurement with two settings of the polarizer by Alice and two different settings in the polarizer by Bob. If you make this measurement, then if Einstein is right, you see, you can get here 16 different kinds of programs. So this photon is carrying the program 1, 0. This means if the polarizer is oriented in direction A1, you get result 0. If you meet the polarizer if the photon meets the polarizer oriented in this direction, produce result 0. And for similar thing for the other photon. If this photon carries the program 1, this means for B1 result 1, for B2 result 1. You can easily calculate this combinatorically, and you have only 16 possibilities. So if Einstein is right, this means you have 60 kinds of different, so to speak, genetic programs determining the behavior of these two particles, of this pair of particles, of these twin particles. And you can I will not go here into the detail of this calculation, but you can build a magnitude S, a quantity S, combining all these possible programs, the possible number for each of these photon pairs, and you build this quantity S. And now the discovery by John Bell is that if Einstein is right and the photons produce the correlations by means of predetermined programs, then the absolute value of S has to be smaller or equal than 2. And in any case, but for certain orientations, quantum mechanics predicts that S is larger than 2. So you see here there is a clash between the view of Einstein and the view of quantum physics. And it is a clash that you can test these alternative predictions on a lab table with the experiment I am presenting to you. So this is the discovery by John Stewart Bell, the Bell inequalities, and that is the key to demonstrate quantum non-locality. Since this discovery by John, numerous experiments have been done, and they confirm quantum mechanics and prove Einstein's assumption of hidden variables wrong. There are no hidden programs behind the correlated events. But on the other hand, you can keep in mind that the measurements happen, you say, almost simultaneously, and so the experiments demonstrate that the correlated events cannot be produced by means of radio signals, because radio signals travel not faster than light. So it looks like the measurement, like the experiment, on one side influences the measurement on the other side, as if Alice and Bob were near each other. It looks like some influence faster than light is really going on behind the scene. Nonetheless, and most importantly, quantum mechanics prevents us from using such an effect to phone faster than light. That is amazing. Well, these kind of experiments have been awarded with the Nobel Prize in Physics 3 years ago. The Nobel Prize went to John Clauser, Alain Aspect, Anton Zeilinger, if you want, representing a larger number of experiments on entanglement which have been done, with all the merit certainly for these three scientists. Once again, they were awarded 4 experiments with entangled photon, establishing the violation of Bell inequalities. These are the experiments by these 3. This experiment left a question open. The question is, can the correlation between the results of Alice and Bob be explained by a cause and effect relationship? That is the question I asked to John Bell in a seminar organized at CERN in Geneva in January 1990, and that is because I organized this colloquium with John that I am speaking to you now here, because there in this colloquium I was inspired by John Bell to perform, to do the before experiment. Some months later, uh, um, in May 1990, same question was discussed in Cologne, in Germany, again in a seminar, in a meeting with John Bell, and this time was also here Anton Zeilinger. So John Bell, the discoverer of the Bell inequalities, and Anton Zeilinger, one of the Nobel Prize winners for having demonstrated violation of Bell inequalities in nature. So this was an amazing coincidence. In this, actually, I would say, if John were alive, he had surely won the Nobel Prize, also with the experimentalists. But this was well. What is the before experiment? It is a combination of relativity and quantum physics in the same experiment. So it is the Bell experiment, but setting the polarizers, the beam splitter in movement. You see? If you have this experiment with measurement devices in movement, then you can have that the choice here in this beam splitter happens in the if this beam splitter is moving and this is at rest, the simultaneity line is this one. So the choice here happens before the choice here. But if this beam splitter is moving, then the simultaneity line tilts, and the choice here happens before the choice here. That is the before timing. And you can get this condition with enough larger velocity and enough larger distance, but not excessively large. Unfortunately, John Bell died in October 1990, and so I could win a Swiss banker, Marcelo Die, a private banker, to fund this experiment. And we went to Anton Zeilinger to discuss with him the experiment in Innsbruck. At this time, he was in Innsbruck. And this was very nice collaboration. We were quite, Anton has helped us to set the experiment. But finally, the experiment was done in Geneva by the group of Nicolas Gissen, because in this group, the setups were convenient to set beam splitters in motion. You have here the setup, and you see as motion, beam splitter in motion, we used sound waves traveling at 2.5 kilometers per second. When some wave traveling here, so, and when some wave traveling here, so. With this setup, we could get the before condition. And the experiment was done in 2001, and here is part of the group, and here is you have the, now he is a professor in University of Bern. Andrei Stefanov was realized as PhD the experiment, and here on 22 June 2001 at 9:30, André presented the results confirming that the correlation didn't disappear in accordance with the quantum mechanical predictions. So the before-before experiment proves that or rules out an explanation by causality in time. So the view that one of the correlated events is the cause before in time and the other the effect after in time. The correlated distant events build a single non-local effect popping up, materializing in the space-time, but the cause is beyond space and time. You can say this experiment confirms the principle Q, that is, not all what matters for physical phenomena is contained in space-time. Or, as it were in the wording of Nicolas Gisin, quantum correlations come from outside the space-time. So the experiment was received this way in the popularizing media. The time doesn't exist, or in science, spooky twins survive Einsteinian torture, and so on. Well, an interesting book is the book by Cija Merali, dedicating the second chapter to this experiment, and with the conclusion you have seen in my title, The Quantum Realm Beyond Space and Time. I would say a good way to summarize also these results regarding quantum entanglement is the statement by Anton Zeilinger, one of the Nobel Prize winners: space and time are secondary constructions. So the visible world where we live and in and move cannot be explained alone by means of visible material causal chains in space-time. We can help acknowledging invisible causes acting from outside space-time. And then you can ask, what is beyond space-time? Which kinds of beings are these invisible causes? John Bell asked already in this colloquium in 1990, correlations cry out for explanation, he stated. And well, I could say the search for explanations is undoubtedly stimulating our imagination and creativity. A quite important theorem is the free will theorem by John Conway and Simon Coshen. And this theorem I actually says that if you accept experimental freedoms, that is, if you accept that we experimenters can freely set choice between orientation A1 and orientation A2, then there is particle freedom, that is, the particle choose as freely as us to produce result 1 and result 0. So you see, this is a way to say that behind entanglement, we have to admit some kind of freedom in nature. Well, I say it doesn't make sense to state the particles have free will because the particles are actually the particles are materialized in space and time. So, and we have say something has to come from outside space and time. So I think, and the best way to express the free will theorem is by stating the general free will theorem, that is, free human beings, we free experimenters, imply free beings outside the space-time producing the results. You can also say free will and consciousness permeate nature. So all here turns around the idea of quantum superposition. And this means before detection, the quantum system is in a state of quantum superposition. And this is not in the state one, neither in the state zero, but in the superposition of both. And this, the Born rule gives you the probability how much will you get one, how much times you will zero. But before the measurement, before the detector clicks, you cannot say the photon is predetermined to give result 1, it is not predetermined to give result 0, is in a superposition. Well, it is this that provokes actually, if you want, the rejection of quantum theory by very renowned people, as for instance, well, let me see before we continue that this idea is an idea which is at the core of quantum mechanics. You have here the formulation by Paul Dirac. There are quantum jumps. A measurement always causes the system to jump into an eigenstate of the dynamical variable that is being measured. That is the quantum superposition, the measurement problem, the collapse of the wave function. So you can get now bright scientists like Gerhard Techoft that some 2 months ago, receiving an important prize, states quantum mechanics is the possibility that you can consider superpositions of states. It is absolutely correct. That is what I'm telling to you. Quantum mechanics is superposition of states. And that is really all there is to it. That is quantum physics. And now, Techoft argues that superpositions of states are not real. If you look very careful, things never superimpose. Could you say, sure, tables, chairs, then superimpose. That is also the famous paradox with the Schrödinger cat. We then see a cat at the same time alive and dead. The cat is either alive or dead. But quantum superposition is the core of quantum physics. Again, another, if you want, another provoking statement about quantum superposition is by Roger Penrose. Quantum mechanics has a huge flow, and the flow is the collapse of the wave function. You can look the video. He goes, Roger, so far to say that we believe in quantum collapse, or we explain things with superposition. He said we are cheating. Well, you see, these claims reveal actually mental prejudices coming from people who think about quantum superposition states as teeny objects propagating in the space-time like little bullets. But superposition mental states, they are quite common in daily life. When you go to a restaurant, I have seen there is very good restaurants in Calcutta, where you can eat pizzas. When you go to a restaurant or you command online a pizza, before commanding, you are in a mental superposition state when choosing a pizza. Well, you choose, then you collapse your mind to, you say, pizza margherita. Same thing when you are choosing uh, to a gelato fresco. Here, you are before all this gelato, your mind is in superposition. You have to decide and to say this one. Then you collapse the state, the superposition state of your mind. Superposition states before a penalty shootout in the goalkeepers by the kickers in the spectator's mind. When the referee's decision provokes the system to jump into an eigen state. But superposition is quite common in daily life. You are continuously in states of superposition, always we have to decide. The quantum superposition state is so a real mental state. This does not mean that in a quantum experiment, nature is choosing the same way as I'm choosing a gelato. I've been with many gelatos. But the decision nature is taking is quite similar. And the state of nature in before measurement is like the detection of my mind before choosing a gelato. And the collapse means that this superposition is finished, collapses, and then you have a result, you have a measurement. Then, so mental states, but not of human mind states, not human mental states. So, quite interesting. Nicolas Gissen, at the closing talk of the celebration of his 60th birthday, asked, where are there quantum angels who keep track of the quantum register, recording who is entangled with whom? And he writes in his book, there must be some register tracking the status of who is entangled with whom, similar to a register who is married with whom. And he asked whether we have to accept angels who keep track of the quantum registers. Angels in the sense of visible, quite powerful intelligence keeping the track of this register. Another guy pointing in the same direction is Ernst Specker. He's a genius of science and an inspired theologian. He's one with Simon Cochin, one of the who established the contextuality, quantum contextuality, that is the Cochin and the Specker experiments. Well, quantum Ernst Specker, he was professor at the ETH in Zurich. He was the first who told me about angels, and that in some way you need this invisible, quite powerful intelligence to explain nature. So here I am here with Simon Cochin and with the widow of Ernst Specker. I have very interesting information about the spiritual life of Ernst Specker by Susan Specker. Here, Simon Cochin, co-author with Ernst for the contextuality experiment, and co-author with John Conway for the free will theorem. Well, the idea of quantum contextuality is amazingly interesting because this idea allows us to reframe many goals. You have heard yesterday this excellent presentation by David Wallace, and I would like here very briefly, I should have still 5 minutes, by the comment by Andreas Albrecht in Nature, that I found a new way to fit a deity into the picture by identifying the many worlds proposed by US physicist Hugh Everett with thoughts in the mind of God. This is, the hidden assumption behind many worlds is that the physical reality is defined by the free choices human observers can imprisonment perform. So it is not that the universe splits in different parallel universes, where in different universes, in this parallel universe, you get the different possible results. What happened is that all possible human experiments are present in the mind of God with the possible results. And when you make a measurement, you choose which of these goals you want to realize. So you see here, actually, many goals is putting in focus the idea that without human free choices, there is no physical reality. So that is the lab view David Wallace referred yesterday. The lab view is this, is that all the physical reality is a huge lab where take place our decisions. And this is actually the physical reality. So, the invisible quantum realm is in fact a huge mental ensemble of possible outcomes which lies outside space-time in God's mind and contains as an essential ingredient all possible experiments humans of all times can perform. And by freely choosing the settings of the apparatus, here and now, the experimenter actualizes one of the possible outcome worlds and makes it to become visible. The multiverse is a parable of divine omniscience. The quantum superposition state is a real mental state, and paraphrasing David Wallace yesterday, I would say the key principles of these interpretations are: dynamics is not always unitary. When you choose a gelato fresco or a pizza or shoot a penalty, your mind doesn't work unitarily. Measurement, similar thing for nature. Measurement is just a physical process, but it is defined with relations to the capabilities of the human observers. So is how you can define irreversibility. And the quantum classical transition is just the dynamical, irreversible suppression of superposition, and this suppression defines the macroscopic quantum realm. I would like to finish with this quote by Anton Zeilinger. Mysticism is quite a central point on which we can build up. At times, the interpretation, this is already my claim, at times the interpretations quantum physicists convey look as eerie and contradictory. However, all of them have led to scientific progress, as David Wallace stated yesterday very well. And if you listen attentively and put together all what they are telling, these different interpretations, then you get a magnificent contrapuntal polyphony, underpinned by the view that the quantum state is a real mental state, and hence the all possible worlds interpretations. Here you have the contrapuntal polyphony. The quantum realm is not made up of material particles or waves. Rather, it is a mathematical description, a vast cloud of algorithms. The visible material world in which we live is a great calculation processed actually by invisible supercomputing intellects that incessantly project the phenomena we perceive into the screen we call space-time. And consciousness is the interface where the dialogue between this invisible spiritual intellect and us, neuronal intellects, unfolds. Thank you very much for your attention.
Thank you so much, Professor, for that deeply inspiring and insightful session. We may proceed to the questions. The first question by Dr. Bharat Pandey, Government PG College from Uttarakhand is
Question 1. Are we moving closer to a scientific understanding of such a higher reality? I answer, yes. Well, my answer is, look, you are free to choose. You can call this God. You can you can see you can believe in God. You cannot. That is your decision, and you are free for this decision. But what I can tell you is that me as a believer, I can say that quantum mechanics and quantum physics helps me a lot to enjoy God. Okay. And also the other way around. God helps me a lot to enjoy quantum physics.
Next question. So I believe this question, could this suggest that consciousness, perhaps even what some call God, is more fundamental than we imagine?
Well, Evan, I think I have already answered. I think yes.
Yes.
One point would be what you speak about botanic. This is quite stimulating because you can say, well, we are now beginning to discover the possibility of quantum effects in biology. For instance, to explain the chlorophyll function. This could be that to explain, it could very well be that the efficiency of chlorophyll function comes from quantum interference. But we have not yet a well-established experiments to demonstrate this.
Question 3, please. If mind and free will are inevitable, then what is the possibility of having a formal education?
Well, well, that is a very good question. I will say, look, science is pushing us in this direction, inevitably. You have seen that big guys like Tehoft and Roger Penrose, they are, how do you say, astonished about this conceptuality of quantum physics. And well, the astonishment comes because if you think that the quantum superposition and the quantum states are something like objects like chairs or tables, then you will always find that quantum mechanics is where. That is why I am trying to shift the view to this idea that the quantum states are mental states, but not human mental states. Okay? Certainly, our mind functions with such mental superposition, but the mental superposition is also outside our mind in a different form. But you have this idea that nature works with an amazing capacity of calculation and at the same time with an amazing capacity of superposition. That is the amazing thing. And I think science is pushing very strongly in this direction. Question 4, okay. The question 4 was a rather technical question about, well, in the case of the photons, the experiments with photons in entanglement, is not related to spins directly, but to polarization. Okay, but it plays a similar role. But it is the experiments with photons are concerned with polarization, not with spins. Okay. Question 5. Well, for the second, the final question, definitely yet. Yes, definitely yes. These experiments are no longer only physical experiments, but in a certain sense, they are metaphysical ones. So actually, we are performing quantum experimental metaphysics in a certain sense. No? What you relate, what your reference to Kant, this is also quite an interesting point. This deserves to be discussed at length and more in depth. I cannot do this here in the time accorded to us, but one thing I can say, Kant is sometimes ambiguous. For instance, actually, the idea of Kant denying the possibility of demonstrating, of proving free will or is very much related to his idea of causality. For Kant, causality is in space and time. It is the causality quantum mechanics experiments disprove, no? Or rule out. But you see, Kant is the metaphysics of Kant is a moral metaphysics because he gives very most importance to the moral law, and then he says this moral law comes not from us, but from outside. So you see, if he would live now, and he had now the results we are getting, then I be sure he would correct his criticism to the metaphysics, precisely to found better his moral proof of the existence of God. So it is a very interesting point that has still to be worked out.
Thank you, sir. The next question by Shravan Kumar.
Well, I have to say I am not familiar with these experiments. I would be thankful if you send me a reference. Well, I cannot respond because honestly I don't know these experiments.
Yeah, thank you so much,